At high temperature and low density, particles fill up the energy states according to a rule called Maxwell-Boltzmann statistics. In this rule, all possible arrangements are included and the particles are considered distinguishable because they possess sufficient energy to stay apart. We can therefore count them, identify them, and treat them as separate entities, even though they are identical in nature. We now move on to the situation when the temperature of the system is low, say near absolute zero. In this case, the rules that the particles follow are called quantum statistics. At low temperature, particles do not possess large energy and therefore cannot remain far apart from one another. If the particles are identical, they become highly condensed, coming so close that we can no longer distinguish them as separate entities. We cannot follow their individual motion or track them in any meaningful way. In other words, particles become indistinguishable. We can no longer assign them different names or labels. If one particle is represented by a red ball, then every identical particle must also be represented by a red ball, because no distinguishing feature remains between them. If two such particles exchange their positions, we cannot tell that anything has changed. The system appears exactly the same because the particles are identical and inseparable in identity. This indistinguishability leads to the rules known as quantum statistics. Consider two energy states E1 and E2. Let us put one red ball at E1 and the another red ball at E2 to get one configuration. Now, if we interchange the energy levels of the red balls, the configuration is still the same. Clearly, the two configurations possible under Maxwell-Boltzmann statistics give way to only one configuration in quantum statistics. By robbing the particles of their energy, we have effectively reduced the number of available options. In other words, we have lowered the degrees of freedom of the system. Or looking at it the other way round, if energy is made available to the particles, they can explore more possibilities and occupy the energy states in a greater variety of ways. Thus, energy and freedom of distribution are closely linked. The higher the energy, the greater the number of possible configurations. The lower the energy, the fewer the choices available to the particles. Let us now recall the two other possibilities allowed in Maxwell-Boltzmann distribution, namely configuration 3 and configuration 4, where we found both particles occupying the same energy state, either E1 or E2. The natural question that arises is, are these two configurations also allowed under the quantum statistics rules? In other words, we are now asking whether identical particles under quantum rules will tend to cluster together or form a group, that is, stay together in an energy level. The answer is quite simple. It depends on the inherent nature or characteristic of the particles themselves. In other words, some particles naturally prefer to stay together while others inherently refuse to share the same state. So clearly we have to frame two sets of rules, that is two sets of quantum statistics depending on the nature of particles at low temperature, near absolute zero and high density. Now, what are the two rules? One set of particles, namely the building blocks of matter, that is electrons, protons and neutrons, obey a particular set of rules known as Fermi Dirac statistics. These particles are called fermions. Just as mass is a fundamental property of particles, another equally fundamental feature is their spin. Each of these particles possesses half-integral spin. For example, the spin of an electron, proton or neutron is half. There are also other fermions that have higher half-integral spins, such as 3/2 and so on. In fact, any system built of odd number of fermions have half integral spin and hence is a fermion. For instance, 2He3 has 2 protons and 1 neutron, that is 3 fermions, and the total spin is half plus half plus half, which is half integral, and hence 2He3 is a fermionic system. Fermions obey Pauli exclusion principle, which excludes the possibility of 2 identical fermions, say 2 electrons, to sit in the same energy state. Though an electron and a proton can however sit in the same energy state as they are not identical particles. This rule can also be viewed from another perspective. 2 identical fermions tend to avoid each other, that is, they statistically dislike the presence of another identical particle. In simple terms, fermions avoid crowding. This means the third and fourth configurations allowed in Maxwell-Boltzmann rule or statistics do not hold, that is, disallowed in Fermi Dirac statistics. Another set of rules, namely the force carriers or exchange particles, that is the photons, W bosons, Z bosons, gluons, that binds the building blocks, the electrons, protons and neutrons to form matter, obey a rule called Bose Einstein statistics. These particles are called bosons. Just as mass is a fundamental property of particles, another equally fundamental feature is their spin. Each of these particles possesses an integral spin. For example, the spin of photon, W boson, Z boson, gluon are all 1. There are also other bosons that have integral spins of 0 and 2. In fact, any system built of even number of fermions have integral spin and hence is a boson. For instance, 2He4 has 2 protons and 2 neutrons, that is 4 fermions, and the total spin is half plus half plus half plus half, that is integral, and hence 2He4 is a bosonic system. Bosons do not have any exclusion principle, which means no possibility is excluded. So 2 bosons can sit in the same energy state. 2 photons can populate the same energy level. This rule can also be viewed from another perspective. 2 identical bosons tend to coalesce with each other. They mingle, that is, they statistically like the presence of another identical particle. In simple terms, bosons cluster, they form a group and condense. This means the third and fourth configurations allowed in Maxwell-Boltzmann rule or statistics hold, that is, these are allowed in Bose Einstein statistics. Let us mention the rules or the 2 statistics in mathematical form. This is Fermi Dirac distribution obeyed by fermions, that is followed by particles like electrons, protons, neutrons, etc. This is Bose Einstein distribution obeyed by bosons, that is followed by particles like photon, W boson, Z boson, gluon, etc. Also, Maxwell-Boltzmann distribution valid at high temperature and low density reduces to these quantum distributions depending upon which particle is under discussion. This can be proved mathematically. Here, average n represents the average occupancy, that is how many particles sit in an energy level. Beta is 1 by kT, where k is Boltzmann constant, T is temperature of system near absolute zero, mu represents chemical potential, which is the energy that system gains when a particle is added, and E is energy of level or state.